Hi, we will continue our regression modeling, a couple of lectures, and you can think it as a continuation of like what we have discussed in our last class. So I'll be taking a few real world data sets to actually unwrap a few important concepts that you will need to master if you want to really good in predictive modeling. And again, although we are doing regression for now, but most of the things will apply to other machine learning problems, more specifically to a classification task. So the first notebook I'll be demonstrating for a regression problem, that is to predict the health status of some diabetes patients. And in this part of the lecture, we'll be comparing a few models. We have talked about linear regression in our last lecture, but we'll be comparing the results with three other models, namely random forest, support vector regression, and boosting. And as I said, that as we progress, we'll be learning about some important concepts such as model overfitting, and we'll be also learning about a specific strategy, what we call k-fold cross-validation. So as usual, we'll be loading some of the packages, NumPy pandas, and if you recall, we implemented the regression model by our own in our last lecture and the content that I have provided. But here we'll be using some of the packages developed by the scikit-learn community and also other models. For example, the random forest regressor, gradient boosting regressor, and support vector regressor. So we are loading corresponding packages here. We'll also be using the dataset curated by scikit-learn. We will also be using some metrics, especially one specific metrics, what we call mean squared error, again from the scikit-learn package. And for visualization, we'll be using Plotly. So let's load the packages. And here I put the link of corresponding dataset description. So if I go to the dataset, we'll be looking at some of the features, but here the target variable or maybe the response variable is a quantitative measure of disease progression, how the diabetes is actually increasing over the time, for certain patients. So here, let's load the data set. Data frame is under df.data, So let's look at our data frame. So df data and head, this will give you the data frame, and you can see that the values, first column is age, sex, body mass index, and some other features. So if you just load in this way, that dataset dot load diabetes and return underscore x underscore y equal to true. So two things. One is that you can load the data as a data frame and format is as you require, but you can also ask this method to give you in the NumPy matrix format, that we will need to train our model. So we can see that the features matrix is actually 442 times 10, the matrix, and for the 442 data codes, we have 442 levels, And here I'm plotting one specific feature, that is BMI, and if I plot, you can see as the value of X, that is that the BMI increases, you are actually having some more trouble in terms of your progression of disease. Okay. One thing to mention, if we go back to this data frame, one thing may strike you that why the values are actually showing this pattern, especially if you look at age, then you have a negative value and the values are less than 1 and even negative. The same applies to the sex column. But let's not worry so much because this is due to normalization that we'll be learning in another video. These data are actually normalized data that we're looking at. Let's recall again. So we have 442 entries, 10 features, and 442 levels, and here we are just plotting one specific feature. So here I'm splitting the data. So I'm splitting into train and test buckets that we'll be explaining a little later more. But you can think it as I'm just getting half of my data matrix in one matrix and the rest in another matrix, and likewise the levels, And here I'm instantiating my linear regression model. And then what you have to do, you have to fit your model by passing your features, training features, and the training levels. So if I do that, then I will have my model, and we can look at it. What we're saying that you have 10 coefficient and 1 intercept. And if we go back to our previous presentation, if you recall, for the height weight relationship model that we learned last time, so we had one feature variable and one response or target variable, but we ended up with two parameters. So one parameter is actually tied to my input feature. The other one, what you call intercept or bias, so it doesn't have any dependency with the input features, So for one variable, we have two parameters, beta 0 and beta 1. So we can quickly connect that as we have 10 features here. So we'll have 10 coefficients, regression coefficient, and one intercept, So this linear regression model has 11 parameters, okay? Now, as you have a model and we have our test data, we'll get our prediction, and we are comparing our prediction with our test set by using the mean squared error function provided by scikit-learn matrix, If you do that, then you'll get some numbers, So this is one thing we will use frequently. So this is the mean squared error. Up to now, we have our linear regression model. We trained with half of our data matrix, and we are testing with the remaining half, and this is our error. The number is close to 3000 mean squared error value, okay? And next, we will run through a random sampling, Here, we will use the scikit-learn function train test split. If you specify the test size, for example, I am passing 0.1, that means that I want to actually grab 10% of data as my test data, So let's run this. So you see, we got about 400 records as my training data and 45 records as my test data. So you can change this value. Now I want 20% of my data to be used as my test data, So here I am actually writing a wrapper class, my regression model. So the whole idea is that if I want to parameterize by a specific model and instantiate this class, and I want to actually iterate. So here, let's run this. So again, here, this is a wrapper class to iterate over experiment by instantiating different models, So here I am actually instantiating my regression model, and I'm parameterizing the linear regression model as my parameter, just the model that we used in our last experiment, okay? And this is the scikit-learn implementation, So this will give me a model that is actually a linear regression model, and I do the training and then I do the testing, okay? So you can see that the train error is around 2700, and the test error went to 3400, But again, these numbers are mean squared error. And again, this is for a 80% training and 20% test data. Then we'll learn today another concept, what we call cross-validation error, okay? Or cross-validation score, Okay. So let's assume that we have our data and we want to actually run a threefold cross-validation. So the whole idea is that you will split your data into 3 equal parts, and then you will use part of your data for training and then the rest as testing, So here, this was the entire data. I split it into 3 parts, and now I am using the last part as my test data and then the first 2 parts as my training data, So you have 3 splits. First, we'll take D1 and D2 as my training and then D3 as test. In the second case, we are using D2 and D3 as my training data and then D1 as test. And for the last case, I'm using my D1 and D3 as my training data and D2 as my test data. So it's kind of a randomization of your data and run your experiment over a number of times, So this is what we call k-fold cross-validation, and this example is for a 3-fold cross-validation setup. Okay, let's go back to the notebook. So you can see that we run 3 times, and these are my validation scores. Let's not focus on the negative, because here we are talking about score, not the error. So that's why we put a negative sign here, because the score should be the higher the bigger. So this is better than this one. Okay, and let's look at their mean and standard deviation of the errors, and you can see that the error, or maybe the score, is within the range around 3000. That matches with all our experiments. And let's look at the standard deviation as well. So here I'm doing the same experiment, but if you look at, I am parameterizing a random forest regressor here now, and let's run the experiment. Here what we see, that the training error, if you look at the training error, were in the range of 2000. So if you see, the random forest training error is very low, and if you look at the test error is close to 4000, So here one thing we can explain, that the training error is way less than the test error. Difference between the training and test error is too high. So one thing we can come up with as a message, that here the model is actually overfitting. If you do the cross validation, we see the mean of the error is around 3000. Okay, we can do the same for support vector regression, and here both training and errors are way higher than random forest and also the linear regression model. Okay, and finally we'll do the same for boosting, and here the results also doesn't look that good. Okay, we are not coming to a conclusion, because we have some other things to complete before we compare these models as an apple to apple comparison. But one thing you might have heard, that the linear regression is a simple linear model, and the random forest or support vector machine, these are actually higher capacity models. So for this particular example, one of the assumptions might be that the number of data points are too small. We are working with something around 400 data points. So far, as with the base setup, we see that the linear regression model is actually doing fairly good for this particular case, But we will move on with other setup where we will try to convince ourselves when to use linear regression model and when to use other kind of models. Okay. Thank you.